Great. So welcome everyone for today's DMAP seminar. Today we have Aaron Williams giving a talk, and I want to just say a few points from his CV. So he did his PhD at the University of Victoria in 2008 under the supervision of Frank Rusky, and then he has been a postdoc at several places until he became assistant professor at Bard College in Simon's Rock. And after that, he founded his own college, namely Williams College, where he's now assistant professor and has the email address aaronwilliams@williams.edu. And today he will talk about the Bruijn sequence constructions. So please, Aaron.
Great. Thank you for the invitation, Torsten, and for the nice introduction. And thanks to everyone for attending. I understand it's a very busy day of talks at your location. So thanks for making time for one more. So we'll talk about de Bruijn sequence constructions, old and new. You know, when I think of universal cycles or de Bruijn sequences, I sometimes think of bicycling. Did you know that there's sort of major bicycling history in your area? So if not, you should look up the name James Starley. I think it was shared on the website, but if you want to follow along with the slides, there's a link here, tiny.cc, DIMAP, and then the date, 28 June 2021. Okay. When I think about bicycling, sometimes I also think about a shared experience Torsten and I have, bicycling through Chile, not at the same time, but an interesting intersection nonetheless. It's kind of interesting to think of how bicycle technology has improved over the last 100+ years. And this talk will be looking at how de Bruijn sequence technology has improved over the last 100 years. Okay. So the outline of the talk, we'll introduce the idea of de Bruijn sequences, and we'll give 5 different construction strategies. And for each strategy, I'll try and throw in some personal remarks and stories along with the results. So first, we'll introduce the concepts for binary strings, carry strings, different types of permutations, weight range. Then we'll talk about Hamilton cycle construction, Eulerian circuit construction, linear feedback shift register construction, a greedy algorithm, and necklace concatenations. So let's get it started with some basic definitions. So a de Bruijn sequence, or a de Bruijn cycle of order n, is a circular binary string of length 2 to the n that contains every string in Bn exactly once as a substring, where Bn denotes the set of all binary strings of length n. So here's an example. This is a de Bruijn sequence of order 6. So it's a string of length 2 to the 6, and it contains every binary string of length 6 exactly once. For example, if I look at this little window here, I see the string 110001. Okay, and so all of the strings are packed in like sardines, so to speak, around this cycle. And de Bruijn sequences exist for binary strings of length n for all n. And during the talk, I'll frequently refer to a special de Bruijn sequence called the granddaddy de Bruijn sequence, and that's the lexicographically smallest one when you view it linearly. Okay, so speaking of linearly, here is the granddaddy de Bruijn sequence of order 4. And of particular note is that the last substring, so the first substring would be 0, 0, 0, 0, and the last substring is 1, 0, 0, 0. Do keep in mind that the substrings wrap around as if this was written in a cycle. Okay, another concept that will be helpful is that of decoding a de Bruijn sequence, and that refers to writing out the substrings one after another. So if this is the de Bruijn sequence we're thinking about, then the first substring is 0, 0, 0, 0, as mentioned. Then the next one is 0, 0, 0, 1, and so on and so forth. Notice that new bits are shifted in on the right. And again, the last one is 1, 0, 0, 0. Notice that this list of decoded strings has a nice closeness or a gray code property. So if we have, just looking at n equals 4, if we have some binary string b1, b2, b3, b4, then what is the next binary string in this decoded order? Well, everything gets shifted to the left. So now it starts B2, B3, B4, and we either shift in a 0 or we shift in a 1. So that means we have an order of binary strings that obey this closeness condition. The same idea generalizes naturally to other alphabets. So a k-ary de Bruijn sequence of order n is a circular string of length k to the n that contains every string in skn exactly once as a substring, and we'll let skn be the set of all k-ary strings of length n. So for example, here we've got 3 different colors. This is a 3-ary de Bruijn sequence of order 4. So if I look at one window of length 4 here, I've got 1, 2, 3, 1, and all of the different strings are in there exactly once. And these generalized sequences exist for all k and n, and they have lots of interesting applications. In this talk, we're specifically interested in how to make de Bruijn sequences. So how can I make one of them efficiently? Okay, this one here again is the lexicographically least, and it's called the granddaddy. So let me introduce 2 other types of de Bruijn sequences. So what if we don't want all binary strings, but we only want the strings that have a certain range of weights, where weight refers to the number of ones? So let's let b and w be the set of binary strings of length n and weight w. So for example, 4 bits with 2 ones, that would be this set here. A weight range de Bruijn sequence of order n is a circular binary string that contains every string in bn L for the lower bound, U for the upper bound, exactly once as a substring, where this set is just equal to the union of the individual weights. So for example, this here, it's a de Bruijn sequence of order 7 with weights being 3 or 4. So if I look at a particular window here and a length 7 string, then I get one of the possibilities in there. And these things exist so long as the lower bound of the weight is strictly less than the upper bound of the weight. In other words, they don't exist when the range contains just a single weight. And I'll show you why that's the case using a different object in the next slides. So let's think about what a de Bruijn sequence for permutations would look like. So, well, first of all, they don't exist. So let P of n be the set of permutations of 1 through n in one-line notation. Universal cycles, so that's the term used when we generalize beyond k-ary strings. So a universal cycle of Pn doesn't exist when n is greater than or equal to 3. And why is that? Well, let's consider n equals 4. So if we did have a universal cycle for n equals 4, then somewhere we'd have 1, 2, 3, 4. Okay? So we've got this window here. Let's think about what the next window would contain. Well, it starts off 2, 3, 4. So there's actually no choice for the next symbol. The next symbol has to be 1. And more generally, you never have any choice, and you just end up spinning around the same or cycling over the same set of rotations. We'll refer to Pn and Bnw as sets that have fixed content. So in other words, the strings all consist of the same multi-set of symbols. And more generally, we can form a set of fixed content strings by specifying the frequency of the different symbols. So we'll say here C, F1, F2 up to Fk. That means there's F1 copies of 1, F2 copies of 2, Fk copies of k. Okay. And permutations are the special case where all the frequencies are 1, and the fixed weight binary strings are the special case where we have just 2 symbols. And we'll refer to these as fixed content strings, also known as multi-set permutations, also known as strings with the same p vector. And universal cycles don't exist for these fixed content strings unless it forms one rotation class, which we'll refer to as a necklace class, and we'll define that a little later. So let's focus on this case of permutations again for a minute before moving on. So we've said that they don't exist, but there are other ways we could consider packing in the permutations of n into a single cycle. So we'll mention 3 approaches here. One is called a super permutation, and in that case, we allow repeated or invalid substrings. So the idea is we want all of the permutations in there, But the thing that has to give is that we may need more space than n factorial. Okay, and that's going to result in strings that aren't necessarily permutations, or permutations that are repeated more than once. And the goal is to find the shortest super permutation. Order isomorphism. So instead of encoding the permutations directly, we can use a larger set of symbols, so more than n symbols. And then when we're looking at an individual window, we use the relative order of the symbols in that window to encode the permutation. A third option is to use a shorthand representation. So instead of looking at the length n substrings, we only look at the length n-1 substrings. And the reason for that is that the final symbol of a permutation is redundant. More generally, there's redundancy whenever you're working with a fixed content language. So here's some examples for each. So, 3 factorial is 6. This cycle here has length larger than 6, but it does include every single permutation at least once. This is an example of the second one. So in this case, we're using 4 different symbols to encode the permutations of 3. So in particular, 1, 4, 2, that would be interpreted as 1, 3, 2, because that would be the relative order. And by using 1 extra symbol, that's actually sufficient for creating one of these universal cycles. And in the last case, we don't use any extra symbols, but when we're reading or decoding the sequence, we only look at the first 2 symbols instead of the first 3. The latter 2 are referred to universal cycles because they are packing a certain set of strings into a particular space, whereas the first one is not considered to be a universal cycle. The third one, personally, I think the third one is the nicest because it has a nice advantage when you decode the strings. So let's just look at an example here. So let's decode this sequence here. So the first 2 symbols are 1, 2. Then we infer the last symbol 3. In this case, the next symbol happens to match, but that won't always be the case. Next, we have 2, 3, and the missing redundant symbol is 1. Then we have 3, 1, and this is a case where the next symbol is not what the inferred symbol would be. So the missing symbol in the permutation starting 3, 1 is 2. Okay, that's where we're getting the flexibility, but in a different way than using a larger symbol. Okay, and continuing on like that. And you'll notice that in general, what happens, and again, using an example for n equals 4, if this is one of the windows, so P1, P2, P3, and P4 is the inferred symbol, then the next permutation will be one of 2 things. It'll either be a full rotation, like P1 moves to the end, or it will be a prefix rotation of length n-1. So in this case, the P1 moved into the second last position. So you notice that here, where the missing symbol stayed on the right, and in the other cases, it was a full rotation. So you get this nice kind of gray code order when you use the shorthand representation, and you don't get anything like that in the other 2 cases. So more generally, we could talk about universal cycles for fixed content strings. So here's the special cases of a permutation or a special case for fixed weight. In both cases, we're underlying the inferred symbol. Or more generally, we could think about these for the permutations of any multiset. So here's an example for the multiset 1, 1, 2, 2, 3, 3, again, with the 1 symbol inferred. Prior to this year, let's say, there were known constructions for this case and this case. Okay, and we'll see those later in the slides. So our goal, besides going through the history, the other goal for this talk is to figure out if we can generate this type of universal cycle efficiently. I'll direct you to a couple of websites. So there's bruijnsequence.org. That is created primarily by a colleague of ours, Joe Sawada. And most of the things that you'll see in this talk, you can get some reference to on that site. This site was actually sort of a copy of another site created by Torsten called the Combinatorial Objects Server. So this site is focused more on gray codes. We'll see sort of the prototype gray code a little later in this talk. And that term refers to minimal change orders of various combinatorial objects. So this particular order of the permutations of a multiset will come up later. You may have heard of Torsten's famous solution to the middle levels conjecture. That's on the website as well. And the site is named after the original combinatorial object server, which was created by my PhD supervisor, Frank Ruskey, and Torsten sort of revived this project and expanded upon it. And there's the Wizard of Cause, who exists only on the Internet Archive now. So now let's move into construction strategies. Okay, so we'll go through 5 constructions, and this is a very modular 5 sections. So, you know, if you find yourself wandering off with your attention, I'll make sure to announce when we've moved on to a new construction. So it's not cumulative, each one is sort of separate in a sense. And that will be the structure of the rest of the talk. So first approach, and this is, historically is not like the first approach, but I think it's the easiest one to, it's maybe the most understandable one, at least in my view. So we're going to talk about Hamilton cycles and cycle joining. So consider the following graph, which is known as the Bruijn graph of order n. The vertex set is the set of binary strings, n-bit binary strings, and there's directed edges from each binary string to the binary string that's shifted to the left and with 0 or 1 joining in. So just like we saw how one window or one binary string in the decoding changes to another, we model those with directed edges. Okay, so you either shift in a 0 or a 1. This is what the graph looks like for order n equals 4. And it's pretty clear to see that de Bruijn sequences are in one-to-one correspondence with Hamilton cycles of this graph. You know, that observation, though, isn't particularly useful, right? We don't have any nice categorization of Hamilton cycles, and finding one can be difficult, right? So this is not particularly useful by itself, but we can make it useful by thinking about it a little more. Before getting into that, this is an alternate embedding of the de Bruijn graph of order n equals 3, which is pretty cool. So yeah, very beautiful drawing of that. Okay, so let's talk about cycle joining. So a common approach to building Hamilton cycles is to cycle join. So you start with a basic cycle decomposition. In other words, every vertex is in exactly 1 cycle. Then you try to merge cycles together into larger cycles, and you keep doing this. Okay, so let's think about what we could do with this graph. And I'll mention, you know, identifying a suitable initial cycle decomposition is very important. And when things are working well, you know, the simplest possible case is when the initial cycles can be merged into a spanning tree, and I'll sort of show you how that can be done in this case. So focusing on this graph, one cycle decomposition we can consider is to just use the rotation edges. So remember that there's directed edges from B1 up to Bn that go to B2, B3 up to Bn with either a 0 or 1 shifted in. Let's only consider the edges where the first bit, in other words, the bit that gets shifted out, it gets shifted back in. So these are like rotating the binary string. And if we consider only those edges, we get a cycle decomposition. And in particular, it's a cycle decomposition based on the necklace classes. And a necklace class is an equivalence class of strings on rotation. And when we're talking about an individual class, we let the lexicographically smallest string in that cycle be, or in that class, be the representative. So for example, take a look at this cycle. So notice that we're just cycling or rotating the string around. That's what these edges are doing. So we have the necklace class with these 4 strings, and the representative is the smallest in this set. So the representative, or the necklace in this case, would be 0, 0, 0, 1. Okay, and the necklace classes don't necessarily have the same size. So for example, here you have a size 2 with 0, 1, 0, 1 and 1, 0, 1, 0. So there's a periodicity in these strings, and that's why the cycle is smaller. So let's just look at 2 cycles. Is there some way we could merge these cycles together? Well, yes. If we look at the missing edges, so the edges that aren't rotation edges, there's actually a pair that join the 2 cycles together. If we take and they form an alternating cycle. So forward, backward, forward, backward. So there's like an alternating cycle of length 4 in here. So if we take the symmetric difference of this alternating cycle with the edges that we previously had, then we'll end up with the 2 cycles being merged. Okay. And so hopefully that makes sense. There are these cycles we can merge. We could construct a graph of the necklace cycles or necklace classes and put an edge whenever the necklace cycles can be merged in that same way. Okay. So the graph, another way to viewing this graph and understanding how the merging happens in this case is that 2 necklace representatives are adjacent if you can change a single bit to get from one member of the class to the other. So for example, if I look at these 2, there's actually 2 edges between them, because if I change this bit here, I will get something in this class. And similarly, if I change this bit here, I will also get to something in this class. So we can instead sort of raise up and look at this necklace graph. And the key thing is that any spanning tree of this graph will create a Hamilton cycle in the original, because we're just sort of glomming on cycles together in some type of spanning tree configuration. Okay. And more specifically, the cycles that we get out of this will use the maximum number of rotating edges and the minimum number of complementing edges. So complementing edge means that the bit that's shifted out is shifted in, but the complement version is shifted in. So here's a bitwise view of this graph for n equals 4. So I mentioned that there's 2 bits that you can change to go between these necklaces, and this graph here is more specifically showing if you change this bit, then the bit that changed corresponds to this bit in this necklace. Whereas in this case, if you change the leftmost bit, it becomes the rightmost bit after you rotate things around. So this is looking nice, but it gets a little bit chaotic when we start looking at a larger n. But fortunately, there is always a simple directed spanning tree of these necklaces. So, you know, the spanning tree is not directed, but we can think of it in a directed sense to describe it. So what is the spanning tree I've drawn above? We take 1 to the n, so that's the necklace consisting just of ones. So there's one thing in that. It's going to be the root of the spanning tree. And for all the other nodes, we just complement the rightmost 0 to go to the parent. So in this case, if we're looking at this class, we complement the rightmost 0, and that takes us up to this string. Then we'd complement the rightmost 0. It takes us up to the root. Okay. It turns out that this spanning tree gives us the granddaddy de Bruijn sequence we talked about earlier. So the lexicographically smallest de Bruijn sequence can be understood very nicely in terms of these spanning trees. Okay. It hasn't been very common to think about things this way. So there was actually some new results that we could come up with in prior work in the same way. So there are other simple spanning trees you could create. So for example, make all zeros be the root and complement, say, the leftmost 1 in this case. And that creates a different de Bruijn sequence that we'll refer to as the grandmama, and that will come up a little later. That grandmama paper or research was done with an undergrad, Oscar Hernandez, who got to go to a conference and give a talk. So this was a nice outcome. And then with some more authors, we looked at how to generalize it to K-ARI. If you want to find any of these papers that I put up, you can check out my ResearchGate profile. I tend to use it instead of arXiv just because it gives some more interesting feedback than the arXiv does. Okay, so let's talk about cycle joining for the permutation case using shorthand. Well, actually, we can basically do an identical thing. So we're going to create a graph. Its vertex set is permutations, and we have directed edges based on those 2 possibilities for how the windows differ from one to the next. And then from that graph, we can consider the necklace cycles again. And they form, when you're looking at adjacent necklace classes, you have this same type of alternating cycle of length 4, which allows you to very easily join 2 cycles together. And then you create another spanning tree of necklaces and create another graph of necklaces, and any spanning tree of that gives you one of the cycles you're after. I ended up finding out about this approach because of Alexander Holroyd. So I had come up with an approach and worked through it with my advisor, Frank, when I was doing my PhD. And I reached out to Alexander because I wanted to run some idea past him. And he was like, oh, that result of yours is trivial. You can do it by cycle joining, and then explained how to do it. And then that resulted in a couple of other papers. So we're indebted to Alexander to sort of explaining how to do this cycle joining in a reasonable way. And the reason I got in touch with him is because he is a mathematician that also does change ringing or campanology. If you've ever walked by a church, you may have heard some interesting, bell ringing, not just bringing out the time, but ringing out some type of patterns. Those patterns are actually patterns of permutations. So a famous one is plain Bob minor. And the patterns are based on physical restrictions involving bells. So hopefully the audio will come through here. So I'll play just a short clip here. So they are just warm. So each person is pulling down on a rope that turns one of these giant bells. And they are warming up by just ringing their bell in turn. But after being warmed up, they'll try and start swapping orders. So, the first person will put a delay on pulling the bell, which then moves their bell ring down the order if you're thinking about these as permutations. And similarly, someone may pull their bell faster, which moves their bell one position up in the order. Okay, so there's a limited number of changes that you can do physically when ringing these bells. And I reached out to Alexander because I was wondering if this type of order could be used for this purpose. Okay, and they actually in their group did some, I believe, did some change ringing on one of these patterns. I'd have to ask Alexander. I don't remember the details. I'm not a change ringer myself, but I have seen it live in action once, which is pretty cool. So last comment on this is that a peal is actually ringing all n factorial permutations exactly once. Okay, and this can take quite a long time. So ringing 5,000 changes perfectly. We got this happened first in 1910 and took, over 2 hours. Anyway, so that's an interesting aside about all that. I'll mention before moving off of Hamilton cycles, a more complicated case of cycle merging. So the last two examples were very lucky and simple in the sense that there was a straightforward cycle decomposition, and when we're looking at merging the cycles, we could actually merge pairs of cycles together. Just based on the edges that weren't in the cycle decomposition, they formed these nice alternating cycles of length 4. And so you could take the symmetric difference and you glue together 2 at a time. And then you can glue individual ones onto that. So things are very simple in that case. In most cases, if you're trying this approach, the cycles can only be merged in larger groups. And there may be divisibility issues, which prevents you from merging them into a spanning tree. So if you're merging like groups of 8 together, and then 8 doesn't quite divide into properly the number of initial cycles, then you can't create a spanning tree. You have to create something more complicated. And there might be multiple layers of merging that you have to do to try and get your result. This was the case in a problem I looked at called the sigma tau problem for permutations. So in this case, the underlying, you're trying to find a Hamilton cycle, and the underlying graph, there's 2 types of edges. So if you look at 1, 2, 3, 4 here, you can either swap the first 2 symbols. So 1, 2, 3, 4 goes to 2, 1, 3, 4. That's called tau. Or you can do a full rotation of the prefix. So 1, 2, 3, 4 goes to 2, 3, 4, 1. So it had been an open problem for a long time if this graph had a Hamilton cycle or path. There's a parity condition on n. And in this case, the basic cycles were much more complicated, and all of these sort of complications occurred, but still able to fight through it. This was a paper that I wrote and put on the archive, but had trouble getting published for dumb reasons. And I was thankful that Joe Sawada came in and just took the result and rewrote it from scratch because I was sort of fed up with it, and eventually got it published. So thank you, Joe, for that. Although it doesn't seem like that's directly related to universal cycles, it is actually. These are graphics from Greg Egan's page on super permutations, which I defined earlier. Using this as a basis, you can create a super permutation of a certain length. And it was, or perhaps still is, the record holding one. This idea certainly didn't occur to me, so Greg should definitely get a credit for finding this application of that. Okay, let's move on to the second second construction strategy. So if you're getting a little overwhelmed with the Hamilton cycles, you can start fresh here with Eulerian circuits. And this is probably the most well-known construction strategy. Okay, it's one that you may learn about in your discrete math class, for example. So let's consider again the de Bruijn graph of order n. Remember, its vertex set is the set of n-bit binary strings, and we have these directed edges corresponding to shifting in 0 or shifting in 1. So here we saw the de Bruijn graph of order 4, and here's the one of order 3. We actually saw, remember that interesting loopy picture? That's actually isomorphic to this, surprisingly. So it also turns out that the de Bruijn graphs are related to each other in the sense that the line graph of dbn-1 is dbn. So if you're familiar with a line graph, you use the edges of one graph to be the vertices of the other, and adjacency sort of follows in the natural way. So for example, here we have the vertex 1, 0, 0, and there's a labeled edge 0. That would correspond to this vertex over here, 1, 0, 0, 0 in the next higher order. So if you think through it a bit, it means that de Bruijn sequences are in one-to-one correspondence with the Eulerian circuit. So not Hamiltonicity here, we're talking about Eulerian circuits, so using every edge exactly once. So we could find Hamilton cycles in here, or we could find Eulerian circuits here. And that's very helpful for proving existence because it's easy to see that this graph is Eulerian. So recall, a graph is Eulerian if it's connected, and if the in degree and out degree of every vertex is the same. So every in degree is 2, every out degree is 2 in this case. Okay, and if we're talking about k area, it would be k as the in degree and out degree of each vertex. So just to make sure this is clear, if we wanted to create a de Bruijn sequence of order 4, we could just write out the edge labels of any Eulerian circuit. For example, if we started here, we could go 0, 0, 0, go around here, 0, 1, 0, 0, 1. Oh, I think I forgot to go here, like that. Yeah, so you can create the Eulerian circuit. In particular, you could create the granddaddy if you want. So this was the approach or understanding used in de Bruijn's original paper. So in 1946, de Bruijn wrote about this way of viewing what became known as de Bruijn sequences and used them to count the number that there are, which we'll get to in a minute. It turns out that this was an example of Stigler's law of naming things, essentially. So a few years later, it was found that a previous paper from the 1800s had actually come up with the same number of de Bruijn sequences. And that's just, the way things go often. Follow-up paper, though, however, did extend it to k-area, which hadn't been done before. And more generally, you may have heard of the Best theorem, which is for counting the number of Eulerian circuits in an Eulerian graph. And if you apply it to k-area de Bruijn sequences, this is the number of k-area de Bruijn sequences of order n. Okay, so there's a lot of them. This idea of modeling things as Eulerian circuits was the basis of the first paper to discuss the generalizations under the name universal cycles. And that paper was by Fan Chung, Percy Diaconis, and Ron Graham. Okay, one of the quote applications in the paper is a magic trick that Percy Diaconis came up with involving universal cycles, which I'll mention in passing. They actually, so Diaconis and Graham wrote a book with all sorts of magic mathematics, including the magic trick. And this is a picture from a workshop on generalizations of de Bruijn sequences and gray codes. That's me here on the left. This is my first conference I ever went to. Here's Diaconis. There's Ron up there. A lot of familiar faces for those who've worked in the area before. And Percy is a character. After my talk, he took me aside and he said, "Aaron, I thought your talk was going to be really boring, but it worked out." So I'll explain why that was the case a little later on. And to give you an idea of the magic trick, so Percy, let me rewind for a second. Percy worked as like a busking or professional magician, and is also an amazing mathematician. To give you an idea of his skill set, so here he's got a coin. He can flip a coin and have it land on heads or tails consistently. So more specifically, he can flip the coin and it looks like it's turning in the air, but it's not. He also designed a magic trick that is somewhat like the following. So there's a deck of 52 cards, and he's arranged them in a particular order that corresponds to a universal cycle. So specifically this example, which is a modification of what he did, it's packing all of the strings of length 3 together, where there's at most one descent in the cycle. Anyhow, to give you an idea of the cycle, he'll have 3 people in a row take a card. Then he'll ask them what color is on the card, and he'll maybe ask another question about the relative order, and then he can say exactly what card you have, just because each pattern appears exactly once. And while he's doing the trick, he's sort of running through the universal cycle in his mind. So this is like a magic by mathematics trick that really wowed a lot of full-time magicians, just because it's a totally different type of trick. Okay, so now we're going to move into our third approach for creating de Bruijn sequences, and I'll advertise that this one is going to involve retro video games. So if you've tuned out for a minute and you like retro video games, you may want to come back in. So first we got to describe what a linear feedback shift register. So an n-bit linear feedback shift register has the following properties. Its state is some n-bit binary string, and the next state is obtained by some linear function of the bits. Okay, so it's going to shift in a new bit based on some kind of linear combination of the current bits, and we're working over binary or GF2 here. So essentially what that means is we're taking the XOR of some of the identified or tapped bits. Okay, so there's not too much you can do with a linear function on binary. So let me give you an example here. So in this case, the state of the LFSR is a 15-bit binary string, and we've got 2 identified bits, the 7th bit and the 15th bit. So let's say, I'll explain this polynomial in a second. Let's say the current state is 14 zeros followed by a 1. Okay, what is the next state going to be? Well, this is the XOR gate. We look at the value in the 7th bit and the 15th bit, and we XOR them together. So in this case, 0 XOR 1 is 1. That means that 1 is going to get shifted into the first position, and all the other bits shift to the right. Okay, so this bit that was in B7, now it's in B8. And then we just do that again. Okay, so what would be the next one? The next one would involve tapping bit 7 and bit 15 again. This time 0 XOR 0 is 0, so we'd have a 0 shift in on the left. And we just keep doing that. And we want to know when we get into a loop, basically. Okay. And it turns out, a theorem by Golomb in the 60s is that an n-bit LFSR will visit all of the non-zero states if and only if its feedback polynomial is a primitive polynomial. The feedback polynomial is you just look at the polynomial where you have x to each of the tapped bits. So in this case, x to the 15th plus x to the 7th, and then plus 1. If that feedback polynomial is primitive over GF2, then when you keep iterating over the state, you'll actually go through every single state except the all zero state. Notice that if you only have zeros in the state, then it will stay in the all zero state because you'll always be tapping 0 bits and hence going back to 0, and you'll just keep shifting zeros in. So the maximum we could hope for is going through all of the states but one. And this amazing theorem tells us exactly when that occurs. So why is this related to de Bruijn sequences? Well, if you think about it, we're essentially making a de Bruijn sequence in this case. The only thing that's missing is that we don't have the state of all zeros, but we could just find where in the sequence you have n-1 zeros in a row and insert a 0 there, and you effectively have a de Bruijn sequence. Okay. And what's interesting news is that the sequence of bits, so if you just look at the sequence of bits that get pushed in, they are pseudo-random in various senses. Okay, so they're not the greatest source of random bits, but they're pretty good. So yeah, the sequence here would be 0, 1, 0, and so on. Bad news is that there's no formula for primitive polynomials. You know, just like we don't have a formula for prime numbers, there's no formula for primitive polynomials. So people rely on pre-computed tables, just like, you know, you have tables of prime numbers. There's tables of primitive polynomials. So this is sort of bad news for algorithms in a sense. You know, if you want them to work for all n, there's really no way of just getting one. Okay, so if you say, well, give me a primitive polynomial over GF2 of where n is 1,000, well, you know, you're going to have to do some testing or looking up in some table. So that's a disadvantage. Also, there's no way to create the granddaddy in this approach. The granddaddy is not a good source of pseudo-random bits. Zeros happen before ones, so it's sort of not weighted properly, whereas this doesn't happen with anything created from an LFSR. So David Crane famously used an 8-bit LFSR in the game Pitfall in 1982. The game has 255 screens, one for each of the non-zero states. And the LFSR state bits are used to determine which elements are present on each screen. And then moving left or right on the screen corresponds to moving forward or backwards in the LFSR. So here we've got a picture of Pitfall. If this is the current state of the 8 bits of the LFSR, then you look at the individual bits to figure out what's on the screen. So is there a hole? Are there alligators? Is there a swing? Is there a treasure? So on and so forth. Those come directly from the LFSR, and moving right just increments this to the previous or next state. And that's how the game is generated. Okay. Although this application is widely celebrated, the LFSR code actually takes up about as much space as it would have to just hard code the sequence. So there's sort of a humorous fallacy going on in the history. Like, yeah, David Crane could have just encoded this, hard coded the same thing. A more useful example comes from Carol Shaw's River Raid, also from 1982. It has a 16-bit state, so there's a significantly higher amount of randomization and procedural generation going on in that game. So a professor at the University of Calgary in Canada has been helping make retro game archaeology an academic discipline. I am also trying to follow in his footsteps, but I'm just sort of getting my feet wet and haven't been particularly successful yet. One thing I'll mention is that John has published all over the place on this topic. So, you know, you're delving into an old game, you're reading the machine code, trying to understand things about it. Where do you publish that result? Well, John's published all over the place. So this is an example from the Journal of Contemporary Archaeology. So anyway, that gives you an idea. This is just a new field, at least in terms of academics. So to follow in John's footsteps a bit, I took a look at Donkey Kong, the first NES game, or the first game for the Nintendo's Famicom. And it does turn out that it's generating pseudo-random numbers using a linear feedback shift register. There's no hardware approach to doing this in the early days. However, they totally messed up the implementation. So I don't know if you're super familiar with machine code, but this is the code for tapping 1 bit. This is the code for tapping another bit. And then this is code for rotating 8 bytes. So rotation, and the carry flag is used so that you can shift the entire 64 bits or 8 bytes down the line. Okay, but they did things in the wrong order. So if this was what our 15-bit example looked like, their added bits are all on this side. So if you think about what happens, these bits never contribute to the new bit, okay? They're never tapped. So once a bit goes over here, it's kind of useless. It's just a memory of what happened earlier. So because they put the new bits on this side instead of this side, it doesn't increase the period of the random number generator. So instead of this huge number of states, they only get 32,000 states. And that may seem like a lot, but not if you're incrementing this every frame. So if you're incrementing this 30 times a second, you know, the states are going to run out, and it translates to things repeating in the game about every 9 minutes. You have to do some hacks to stop the timer from you know, killing off Mario, but if you do that, you can observe repeated behavior in certain games that use the same LFSR. So the same LFSR is used in other games. So this is a different form found in Super Mario Brothers. Instead of doing those 8 instructions hard-coded, they have a bit of a loop here that does it. The same code, I've documented a bit more here, found its way into the Famicom disk system. So in Japan, the NES had a disk system. That's what The Legend of Zelda was released on, a disk. And that code is hard-coded into this firmware. And it appears in other games, Zelda, all the way up to the last NES game, Wario's Woods. So using a regular expression for the sequence of opcodes, so load and store, load and XOR, clear the carry bit, branch if not equal, set the carry flag, and rotate. If you make a regular expression for those opcodes and then you search the binary data of these games, we were able to find over 300 matches within the NES/Famicom library. And only one of those games fixed the error. So that's kind of an insight into how developers work. Okay, so last two, these will go a little bit faster. We'll talk about greedy algorithms. So I mentioned the gray code or gray code order a couple times. Some of you are probably familiar with it, but you may not be familiar with a greedy interpretation of it. So the binary reflected gray code is an order of BN in which successive strings differ in just 1 bit, and it can be constructed using a greedy algorithm as follows. So we're going to start with the all 0 string, and then we're going to repeatedly select the rightmost, or repeatedly select the last string in the order, and we'll complement the rightmost bit that gives us a string that's not already in the order. And then we add that new string to the end of the order. So for example, we start here. So this is our order. We think about which bit can we complement coming from the right that will give us a new string. Well, obviously the rightmost bit would work. Okay, now this is the last string in the order. So we look at it. What's the rightmost bit we could complement that gives us a new string? Well, we can't complement the rightmost one. It would take us back here. So the next one is this one. And you just continue on this way, and miraculously you get through all of the possibilities. And this order is known as the binary reflected gray code, where the reflected refers to a different way of constructing it. So let's try a similar greedy approach for generating a De Bruijn sequence. So this first step may take a second to digest, but the idea is we're going to pretend that we got n copies of 1. And then what we're going to do is repeatedly add the smallest bit, i.e. 0 or 1, that doesn't create a repeated substring. So, you know, let me give an example. So suppose we've constructed this much of the sequence so far, and we want to know what the next bit should be. So we say, can I add a 0 to the sequence? Well, I can, or I'm allowed to do that, so long as it wouldn't create a repeated substring. So in this case, the question is, does 0, 0, 1, 0 appear earlier on in the list or in the sequence? Well, it does. So I can't add 0 here, I have to add 1. And it turns out that if you follow this approach, you'll create the De Bruijn sequence that is the granddaddy. Okay, so this is another way of viewing that lexicographically smallest one. The only thing is that you have to remove these preliminary bits at the end. So like they get repeated at the end. And this algorithm actually, amazingly, was discovered in the 1930s, and same idea works for all N and K. So Martin discovered that in the 30s, pretty amazing. It turns out that the greedy algorithm is very flexible, surprisingly so. So if you add the condition that the next substring has to be in the set of strings that you desire to create, then the greedy algorithm works in a bunch of other cases. Okay, so this is an example of various sets of strings that you get these nice de Bruijn sequences for. And de Muro proved a characterization of when this greedy algorithm works. So a very nice follow-up paper by him. Greedy algorithms have also been used to create other types of gray codes. A nice paper that resulted from a visit. I was fortunate to visit Torsten in Berlin, and Torsten and a student he worked with, Hung, were able to push this greedy algorithm really far. And Arturo seems to be, who's on this call, seems to be next in line for pushing this idea further. Okay, the last construction we'll talk about is necklace concatenations. And this is where we can get to efficiency. So I won't talk much about efficiency, but hopefully you'll see that there is a connection between it and efficiency. So let me tell you about an algorithm called the necklace prefix algorithm, also known as the FKM algorithm. So what the algorithm does is it takes an ordered list of strings and it does the following. It reduces the list to the necklace representatives, reduces each one of those representatives to its aperiodic prefix, and then concatenates those prefixes together. So I'll give a fuller example of this in a moment, but the idea is we reduce a big list of strings down to some small sections, and then we paste them together. And we want to know whether the result is a de Bruijn sequence. So amazingly, this approach can be used to construct k-ary de Bruijn sequences of order n. Specifically, you use lexicographic order. And it's possible to implement this efficiently so that you get each successive bit or symbol 1 through k in constant time. So here's a bigger example of this. So the idea is I want a de Bruijn sequence for the 4-bit binary strings. Well, I just start with the lexicographic order of them. I filter that list down to the necklace representatives. So remember, these are the strings that are in their lexicographically least rotation. Then from those, I reduce those down to the aperiodic portions. So 0, 1, 0, 1 just becomes 0, 1. I glue those things together and I get a de Bruijn sequence. And you know what? It's the granddaddy. So another way of constructing this granddaddy de Bruijn sequence. Also interesting, if you use co-lexicographic order instead of lexicographic order, you get a non-isomorphic one, which is the grandmama. This is where the origin of the FKM algorithm came from. So the construction and the efficient implementation of it. Here's Frank, my supervisor, along with Carla Savage. So what if we tried to apply this idea to create shorthand universal cycles for those fixed content strings we talked about? Well, the problem is that lexicographic order doesn't work. So why is that? So if we applied it to permutations, so we're looking at all the permutations of 4. So all the necklaces are exactly the permutations that start with 1. So they're in their lexicographically smallest rotation. Now let's paste them together. Well, we end up getting substrings that are not permutations or not shorthand for a permutation. So 313, that's going to be totally invalid, right? And if we think about the problem, well, we can't have the second necklace followed by the third one. And if we think about what's really the problem, is that this 3 moves more than one symbol to the right. So if I move a symbol more than one symbol to the right in the permutation, then when I look at the concatenation of the permutation, I'll have that symbol twice within a substring of length n-1. So if we want to use the FKM algorithm or the necklace prefix algorithm to create these things, we can't use lexicographic order. Instead, we need to come up with some order where symbols don't move very far to the left. And that may seem like a very obscure topic, but it's one I'm very familiar with. And it's called Kulex order. So this was the talk or the result that Percy was a little skeptical of, but ended up liking. So let me tell you what Kulex order is. There's a very simple rule.
Time a little bit, that we don't go too much over time, please.
Oh, okay. So what, a couple more minutes? Or should I just stop?
I mean, the other talks are supposed to continue now, so if you can maybe. try to come to an end in the next few minutes. This would be good, I think.
We also started a few minutes late.
That's right.
So Kulik's order, here's a rule to change a binary string. Move the first bit to the right until it passes over a 0, 1. Okay. Amazingly, if you just keep applying this rule, you'll go through all of the different possibilities. Okay, and this is the resulting order, a visualization of it in comparison to a lexicographic order. So it's a skew of that. And Kulik's order has been used a lot in the real world. It's been installed in R about 50,000 times a month, which is cool. And it can be used to create these fixed weight or dual weight binary de Bruijn sequences. There's also a generalization to k-array strings. And the main new result is the following. So if we use Kulik's order and the necklace prefix algorithm, we can create a shorthand universal cycle for any fixed content strings, or in other words, the permutations of any multiset. So that's the newest and latest. And the other interesting thing is that you can understand the resulting sequence in terms of a nice tree. The tree is obtained, the tree of necklaces is obtained by swapping the first or leftmost inversion. That's what it looks like, and that result will be presented at the WADS 2021 conference, and that's it. So thank you for your attention, and apologies for going a couple minutes over.
Thanks very much, Aaron. Very nice talk, nice, nice figures and pictures in the slides and stories. Are there any questions from the audience? I have a couple of questions, but maybe we can take them offline, not to extend more. It doesn't seem that there are other questions, but let's maybe, I mean, the three of us can maybe stay for a little longer.
Sounds good.
So thanks very much, Aaron.
Thanks, everyone.
For the talk. And now everybody is invited to join back the other session. Yeah, this was really nice stuff. Especially these